Okay, so we can start the seminar of today. Thank you everybody for being here. The topic of today is Elasto inertial turbulence and numerical discovery, and the speaker of today is Yves Dubief. He holds his engineering and PhD degrees from the Institute of National Polytechnic de Grenoble. His PhD work was under the supervision of Professor Marcel Leseur in the MOST team of l'EGI, Laboratoire des équipements géophysiques et industriels. He studied polymer drug reduction as a research associate at the Center for Turbulence Research at Stanford. He joined the Faculty of Mechanical Engineering at the University of Vermont in 2005. His research focused on high-fidelity simulation of complex fluids and recently multi-fidelity simulations of aerosolized pathogens. So it's with great pleasure that I introduced Yves Dubief, and if I give you the stage.
Thank you. All right, so
now share your screen.
There we go. You see the presentation?
Yeah, we see your screen.
There you go.
Now we see it full screen mode.
All right. So, well, thank you so much, Francisco, for giving me this opportunity. As I said earlier, I very much enjoyed that series of talk, and it's an honor and a privilege to be here. So I want to acknowledge my current collaborators before I start. Rich Kurzweil and Miguel Benitez from University of Cambridge, Jacob Page from University of Edinburgh, Vincent Thierapon of University of Liège, Victor Steinberg from Weizmann Institute of Science, and Björn Hoff from the Institute of Science and Technology. And there are new collaborations that are starting, and I'm very excited for those. I also want to acknowledge the financial support of the National Science Foundation and the Binational Science Foundation, which is an organization that funds United States and Israeli researchers. So the why it's not working? Okay. So why are polymer flows interesting? Well, we all know, because we all live in the world of turbulence research, we all know that polymer flows are, as far as liquids are concerned, probably the best or the most efficient ways to reduce friction drag. The drag reduction can reach up to 80% in pipe and channel flow with only a few hundred to thousands of ppm added to the flow. It's been also a very interesting window, this phenomenon of drag reduction. It's been a very interesting window in the inner workings of near-wall turbulence, because obviously if you have such a small molecule, or a few million of them, that are able to reduce effectively turbulence, learning how that happens can really help us understand turbulence a little better. And by and large, that's what has happened when we finally, narrow down on the mechanism of polymer drag reduction. We found that, unsurprisingly, the polymers were really good at damping vortices by opposing the upward and downward motion that are generated by quasi-spheroized vortices. What's really interesting also with polymer drag reduction is it was found in 1949. Werk established the existence of the maximum drag reduction asymptote, which is basically the minimum drag that a flow can achieve, and it means that it doesn't matter if you increase concentration or change your polymers. This is the limit of drag for that Reynolds number that you can achieve, and this is here into the lower corner that work. Now, interestingly here, close to the critical point, even in 1970, there were some interesting aspects to it, which is we are really at the limit between laminar and turbulence, and nobody really paid attention, thought that it was probably within experimental uncertainties, but in fact, it turned out that it's actually interesting. Well, there is so that's high Reynolds number. At the other end of the spectrum of Reynolds number, in very low Reynolds number, there is the phenomenon discovered by Victor Steinberg in 2000, which is elastic turbulence. So by Grossman and Victor Steinberg. And here, in a microfluidic or in a swirling flow like the one on the left, so basically whenever the streamlines are curved and with the right concentration and elasticity of the solution, concentration of polymers that leads to the elasticity of solution, a chaotic regime can arise. And so Victor called that elastic turbulence, and you see some illustration of it. It increases mixing in microfluidics, so it's really interesting. And Victor, and like this is a very, it is not a well-known fact, but Victor holds a patent on to make mayonnaise in microfluidics, thanks to elastic turbulence. So yeah, this to me, this is quite the achievement, but. So what was the, I want to take us back to when I basically found Elasto inertial turbulence. So the state of knowledge back in 2010 was the following. We knew there was elastic turbulence. At that point, elastic turbulence was 10 years old. Its discovery was 10 years old. We knew that polymer drag reduction existed, that was actually 60 years old. But there is an interesting phenomenon that didn't really attract that much attention and was researched mostly in the 70s, and that phenomenon was called early turbulence. And here you see on the panel on the left some images from the Nature paper from Hoyt in 1977, where it was the flow around that cylindrical object with injection of air in order to visualize the flow. And what happened is that when polymers were added to the flow, Hoyt observed early turbulence or early transition to turbulence. So in 2010, I sort of stumbled. I had missed that paper when I was working on polymer drag reduction. And I stumbled upon that paper and got interested into this. So I used a visit to the Center for Turbulence Research to set up the following simulation. I have a channel flow. At the time, I had a periodic channel flow. And so what I did was I thought, how do I reproduce transition in a channel flow that is as realistic as possible? So this is the setup. I basically superimpose isotropic turbulence to a plug flow and let it evolve over time. So the advantage of having isotropic turbulence in the core is now I can control how much inlet turbulence or turbulence intensity I can inject into the system. I left, as you can see, a quarter of the channel fully laminar for two reasons. One, I was interested in seeing the response of the wall, basically, the polymer dynamic at the wall from the isotropic turbulence without having isotropic turbulence at the wall. So basically a communication issue that I was interested in at the time. I'm still very much interested in to this day. Two, in fact, because it's a plug flow, there are anyway very large gradients that form right away and kill off the turbulence. So, again, it mimics as best as it can an inference flow. I played a little bit with a bunch of initial turbulence intensity and found that the 1.5 turbulence intensity in the absence of polymers was giving the most delayed transition. And so this is what I used with the polymer simulation. So in the polymer simulation, I let the polymer flow field equilibrate with the isotropic turbulence and the general mean flow, and then I start the simulation. So this is what I get. This is the trace. The channel flow is a constant mass flow rate. So basically the pressure gradient varies in time to maintain the constant mass flow rate. And the dashed lines, the dash and dotted lines are the Newtonian flow. So the dash dot line, the one in red, is the one with 1.5% initial turbulence, and it transitions at a time of about 700. The dot line is 2%, and the dash line is 2.5%. The solid line is the polymer simulation started with 1.5% of fluctuation of an intensity. So obviously, this little simulation was able to reproduce early turbulence, but it held a big surprise. And before I go into the big surprise, I want to remind everybody what is Q. So I'm sure that most of you know what is Q, but just in case, I thought it would be good to just remind everybody. Q is the second invariant of the velocity gradient tensor. And so essentially looking at the characteristic equation of the velocity gradient tensor, it is the one affecting lambda, the linear term. And the first variant being the trace of the velocity gradient tensor, and an incompressible fluid is equal to 0. So you all know the Q and R plot that I've shown here. A very popular plot to look at the flow topology. And basically when Q is positive, we are in regions where the rotation rate, here omega ij, dominates the strain rate Sij. And when Q is negative, we are in the reverse position, right? So this is like one example of the vortices. I think, yeah, I have another one. And so this is actually what the turbulence look like with isosurface of positive Q and negative Q in at the Reynolds number. So in a fully turbulent channel flow at the Reynolds number that we're doing this early turbulence experiment. So now let's get back to that early turbulence experiment and show you the surprise, which, when I looked at the flow field very early on into the transition, this is what I visualized. I visualize cylindrical, span-wise aligned isosurfaces of positive and negative Q. And in the fully developed regime, so the blue here are actually positive Q, and the red are negative. So here in the negative regime, what I see is like very large hairpin-like vortices. They are squarish. That's normal. That's the viscoelasticity that makes them square. But I have those trains of, again, alternating sign cylindrical regions of Q. Very much reminiscent of this, but on a smaller scale. So you can imagine that there was a part of me that thought, oh, there is a bug in my code. And that's, as any numerical scientist would know, you are starting to sweat profusely at this point, because you think, okay, so like everything I have published might have that bug. Well, very quickly through resolution checks, increasing the resolution as much as we could, and everything else, it turns out, no, this phenomenon does exist. And this phenomenon is elasto inertial turbulence. So it's, I'm not going to lie, it was really hard to publish, and it took essentially Bjorn Hoff to find elasto inertial turbulence experimentally for me to be able to publish my first paper with Bjorn our PNAS of 2013 on Elasto inertial turbulence, because the community was not ready to accept that this phenomenon existed. But also to me, and the reason why this work has not been published was I felt I needed to understand what was going on here. And one way to understand it is to reduce the problem. And so what I'm going to show you today is really is only 2D simulation. We have reduced the problem as much as we could, but we are learning a lot from it. And we are in fact getting ready to go back to 3D now. So how and why this happened? Why this system was this regime wasn't found? And I'm not going to comment as why it wasn't found experimentally. That I will leave to experimentalists to discuss that. But numerically, I know why, and this is the explanation. So the typical DNS of viscoelastic flows from 1995, that was Bayes and Suresh-Kremer's paper, up to very recently, follow the following principle. So since the flow is incompressible, there was a really strong feeling in the community that spectral methods must be used. The simulation were all made with the type or done with the type of resolution and time step that are used for turbulent flows. So basically, assuming that the dynamic of Newtonian of polymers sort of follows as the same scales as the dynamic of turbulence. And it was acknowledged and recognized that the transport equation for the polymer model causes Gibbs oscillation, but it also was accepted that those oscillations could be controlled by adding tremendous amount of diffusion. So our approach basically when I started to work on the field was to recognize that equation is actually hyperbolic and must be treated with the appropriate numerical method that are designed for stiff equations. So essentially the entire world of compressible flow, astrophysics, magnetohydrodynamics, and so on and so forth. So physically, the diffusion of polymers in water is very small. And this is why the polymer model neglects diffusion. So adding a diffusion term may actually change the physics. So that's a problem. And also one of the issues is that if the problem is stiff, if the equation is stiff, well, small scale can exist and they may be dynamically critical, which means that they require higher resolution and smaller time step. So that's our approach for the past 20 years. And we have new approaches coming up, but I'm going to keep that one secret for now until we finalize all our approaches. We have multiple approaches coming up. Yeah, in light of recent events, I thought I'm only going to talk about things that are in the work for publication or have been published. So here's the polymer model. We start from a polymer molecule that we reduce to 2 bits connected by a spring. And then we average over multiple polymer models like the bead and spring model. And we form a conformation tensor Cij, which is the tensorial product of the end-to-end vector of the springs. And we phase average over a large number of those springs. So basically, the conformation tensor gives you the average, the local average configuration of the polymers. We have 3 main parameters: beta, which is the ratio of solvent viscosity to 0 shear polymer solution. That beta control the shear thinning of the polymer, the shear magnitude of shear thinning of the polymer solution. L, which is the maximum extension of my spring, and the Weissenberg number, which is the relaxation time of my solution. Basically, the time it takes if the polymer are fully stretched and we remove the force that stretched them, how long does it take to come back to coil? Coil is the favorite position, energetic position of the polymers. And the Weissenberg number is a normalized polymer relaxation time normalized by here the viscous flow timescale, but could be normalized by any flow timescale. And this is the key to the model, to the FENE-P model, is a non-linear spring force, and that's the tau Ig. So in terms of the governing equation, those are the governing equations that we solve. The FENE-P model, so on the left-hand side, we have our typical advection term. The term in blue is the stretching of the polymers by the flow, by drag force, by the strain. In light blue, we have our entropic force. And in red, we have the added diffusion. And it's really important to consider that here I write it as 1 over Reynolds number, Schmidt number. The value of the Schmidt number is critical, right? So remember what I said, diffusion of polymer is really small. So we should always aim for the highest possible Schmidt number. And no, Schmidt number of 0.8 is not high. I'm talking about much larger than 1. Okay, so from the flow dynamics perspective, the flow is incompressible. The momentum transport is modified to include the divergence of the polymer stress, right? So this is the contribution of the polymer, that dj to ij. Again, to Tij is defined here as this nonlinear term. And one very important equation, when you take the divergence of the momentum transport equation, you get the Poisson equation for pressure, which includes Q, again, our second invariant, and includes the divergence of the divergence of Tij. So that's kind of my favorite equation. It explains a lot, especially when we go to low Reynolds number, where Q is no longer significant. So in terms of methods, well, this is what we have. So we've worked for the past 20 years, mostly out of non-dissipative, finite difference, or finite volume second-order solvers. We have a couple of solvers. Why do we have a couple of solvers? Well, because I have been very, very anxious and concerned about bugs. And I thought the best way to validate the discovery was to actually, replicate the discovery in totally different code. So we have a finite difference code, we have a finite volume code with slightly different numerical approaches, and they both confirm that. We have other very exciting discovery that I'm not going to talk about, but like basically we are expanding the number of solvers that we are using and simulating EIT with, and we are super excited about that. So then your typical third order Runge-Kutta, and second order, we have a fourth order compact scheme to calculate the divergence of Tij. And for the polymers, the key part is for the advection term, we use an upwind compact scheme. Why? Because it's the reason why the equation is stiff in the first place. So we need something that has inherent numerical dissipation at small scale in order to avoid the accumulation of energy at small scale that leads to divergence of the solution. We used to have local artificial diffusion to help, and in fact, we realized that we could actually totally simulate with global artificial diffusion. In the current simulation, we monitor that the determinant of the conformation tensor is positive everywhere, almost everywhere in the flow. We came to the conclusion that we could have a few points, like less than 1% of the point, and again, think that we have very large resolution that may go negative. And the reason why we've done that is that you can always have 100% of the point positive by reducing the time step. And we've seen no difference with very small time step and large time step. So basically the influence of those few points is negligible on the solution. All right, so let's go straight to the meat of the latest big discovery. In doing 2D numerical simulation of channel flow, of periodic channel flow, we found 4 very distinct regimes. The first one, called chaotic regime, is what I initially found as Elasto inertial turbulence. So here, what am I looking at? I'm looking at a quantity here that is typical of non-Newtonian flow. It's the first first normal stress difference. And it's essentially the difference between the polymer stress in the direction parallel to the principal axis of the elongation of the polymer minus the polymer stress perpendicular to that direction. So how do I obtain that? Well, locally using eigenvalues, I obtain the T parallel and the T perpendicular and subtract one by the other. So by the way, I have checked that I get the same picture looking at elastic energy, which I will talk about a little later. The reason why I like N1, the normal stress, is because it is responsible for the well-known road climbing effect, or the Weissenberg effect in polymer solution that you may be familiar. When you spin a rod into a solution with polymers, the fluid actually climbs the rod, not you don't have the meniscus that you see with Newtonian flow. So here on the left, all those pictures are contours with a log scale, because the values are very large, of this normal stress. And on the right, those are contours of pressure. So in the chaotic regime, we have sheets of very chaotic sheets, thin sheets that contain very large polymer stress. And they result into cylindrical regions of pressure, high and low pressure. Then there is a second regime called the chaotic arrowhead regime. And the chaotic arrowhead regime has this structure right here. I hope you see my mouse. I'm assuming you see my mouse. If you don't, let me know. And this arrowhead structure is found in all the subsequent regime. It's found in the intermittent arrowhead regime. And more importantly, it is found, and it was the big surprise, in the steady arrowhead regime. So the steady arrowhead regime, the steady arrowhead regime, is steady, meaning that this structure does not change. I will show you a video to that effect. And what was astounding to us when we looked at it was really the trace of pressure that is caused by this structure, right? With almost a shock-like structure and a bullet-looking high pressure region, which is inside the arrowhead. Okay, and so now we can go back and look at the intermittent arrowhead regime, and we see that structure, that signature of pressure. But of course, the pressure field is not as well organized because we have significant chaos going on close to the wall, right? And in here, there seems to be an influence of the arrowhead in the pressure distribution, which in that particular snapshot looks like it's creating a large gradient right here. So those are the four different regimes that I'm mostly going to talk about today. And again, I have this compulsion to really always doubt my work. And when I discover something new, think, well, maybe there is a bug that creates all of this. So there has been extensive checks that have been done. So here, like I show you, for instance, the power spectra of pressure at the center line for different resolution. And here, like the effect of the height of the cell close to the wall, which turns out to be quite dramatic. You really need to have a small cell at the wall, otherwise you can have some issues. Well, you basically that will become an artifact. And here the effect of the Schmidt number. Okay, so one thing to notice is that there is no convergence, but we should not expect convergence. We have a mega stiff problem. So the more resolution we get, the more we capture small scales. And in here, it is part of the multiple proof that we've accumulated that there is a very significant effect of an energy transfer from the small scale to the large scale. And so like here on the panel on the right, what I'm showing is actually for my arrowhead, my steady state arrowhead structure. Here I'm showing the imaginary and real part of the modified wave number of the different schemes that I use. So the solid line are the third order Opwin compact scheme, and the dashed line is the staggered second order central scheme. That's so basically here the two negative lines are dispersion and the positive line is numerical dissipation. And the good news is numerical dispersion and numerical dissipation happen really at wave numbers that have little to no energetic effect. So as far as the steady state arrowhead, we are confident that what we are seeing is not influenced by the numeric. It's not an artifact of our numerical methods, right? So again, those are the 4 different regimes of EIT that I'm going to talk about. So here I want to show you a few movies. So this is the first regime, the chaotic regime. So again, those are contours of normal stress. And I'm going to stop that movie because, well, essentially, yeah, it's chaotic. And it goes for long. One other thing that I want to say is that those simulations are really long. The time step typically is 10 to the minus 3 to 10 to the minus 4, depending on the elasticity of the polymers. And I have run all those simulations for thousands of times, right? So some of my simulations I've run for over 1 million iterations. And that's really important because in those flows, yes, there is small scale dynamics, and that small scale dynamic is actually critical to the chaos. But there is also a low frequency dynamic that you need to capture, right? All right, so here I'm going to continue the chaotic arrowhead regime, which is the next regime. And what you can see here is that at any time there is an arrowhead, there is a junction of the polymer sheet at the center that forms that arrowhead structure that we see in the steady regime, okay? But it's very chaotic, still very chaotic. And there are some really cool patterns here that we still have to investigate. All right, so let's move to intermittent arrowhead regime. So here what you're going to see is that at time, the flow becomes steady. Like right now, it's slowly going towards steadiness. The chaos near the wall is starting to disappear. The arrowhead is more and more symmetrical. And then you will still see activity reforming close to the wall and a breakdown of the symmetry, a breakdown of the arrowhead that is happening right now, okay? And then for the steady state arrowhead, well, so this is the simulation. This is one of the simulations that I'm sort of ashamed of because it's a 2D simulation, like all the simulation, right? You think I'm using a supercomputer to run a 2D simulation. So that's why I felt better last week when I saw Professor Jimenez showing 2D simulation. But on top of that, just to ascertain that I really have something steady, I ran that simulation for 10,000 non-dimensional time. Again, with a time step, this one was probably 10 to the minus 4. So you can imagine, right? How long it took. So here, in this simulation, you're going to see 2 simulations. You're going to see the panel on top is the same type of movie that you've seen in the past 3 movies. Basically, I'm just showing you the normal stress XZT. The panel at the bottom is actually every flow field is shifted by the convection speed of of the structure, which is the center line velocity. So we've confirmed that by a couple of ways with space-time correlation, and also another way that I'm not going to get into with optimization. So essentially, if it's totally steady, the bottom panel should not move at all, and it doesn't. And I can promise you that I did not, freeze the frame below. I literally did a spectral interpolation of each snapshot, the snapshot that are seen above, by UCT in order to recenter, to eliminate the convection sphere, right? So that's a nice visualization of the steadiness of this arrowhead structure. I want to restart this. So what are the effects of the different regime on drag? Well, all those regimes produce drag increase that we call DI in those graphs. And you can see the trace over time of the different regime. So again, on the right, I have the color code, green being chaotic, orange being chaotic arrowhead, blue being intermittent arrowhead, and obviously the magenta being steady state arrowhead. So I also plot the mean drag increase as a function of the Weissenberg number, just to see if we see some type of pattern, and we do see some type of pattern with here sort of a maximum for those curves. Again, like we need a lot more points to draw some conclusion, and also have a phase plot of the states as a function of Weissenberg number and L, the length of the polymer. And essentially the chaotic regime tends to be for lower L or lower Weissenberg number. The gray plot, by the way, are laminar solution, okay? So here, what's interesting is that as we increase the Weissenberg number and keep the size of the domain constant, we get to laminar flow, okay? It's really important here to understand that we approach the laminarization by increasing Weissenberg number, which is different from what my colleague Björn Hoff has done, where he approached transition from turbulence from low Weissenberg number, increasing the Weissenberg number, okay? So here, moving to what the mean velocity profile look like. Well, as we get more into the arrowhead dominated regime, we have more of a plug flow. And for those of you who are working on polymer flows, I just show you the mean trace of the polymers. Again, like right now, this is not relevant so much to our discussion. What is very much of interest to me, and I just saw Professor Vasilikos entering, and he had a really nice paper, I think back in 2010, 2011 on energy transfer. So one of the things that we know in the community is that if you look at the transport equation of the turbulent kinetic energy and the turbulent, the transport equation of the elastic energy, there is one common term, and that's the Tij, Sij. So that term is the energy transfer, and what I'm going to show you is the turbulent energy transfer. So the prime are for the fluctuating part of Tij and Sij. And based on those equations, what you see is that when pi prime E is positive, it means that we are taking energy from the turbulent kinetic energy to increase the turbulent elastic energy, and obviously vice versa. When pi prime E is negative, the energy goes from elastic energy to turbulent kinetic energy. So in these slides, what I'm plotting is the co-spectra of TS of pi prime E. So the axis is the wave number in the x direction. So I compute the co-spectra in the x direction, and in the in the vertical direction, I have the distance from the wall, 0 being the wall and 1 being the center line, okay? So again, as a reminder, where it's positive, the flow gives energy to the polymer. Where it's negative, the polymers give energy to the flow. And what you can see, and here everything is normalized by the Kolmogorov scale at the wall of the flow. But what you can see is that the transfer of energy from the polymer to the flow in the chaotic regime is mostly at a smaller scale than the transfer of energy from the flow to the polymer. And it's only in the arrowhead regime that we have a reverse situation, okay? But, this is what we suspected all along, and this is why it's really important to run those simulations with the highest Schmidt number you can, your code can accept, is because the energy transfer from small scale to large scale is absolutely critical to the AIT phenomenon. So in terms of checking the robustness of the steady state arrowhead regime, well, we naturally, for instance, first increase the size of the domain, because we acknowledge that in a periodic channel, the size of the domain basically limits the wavelength that you are actually simulating. And so, for instance, starting from a simulation of at L equal 100, Weissenberg of 100, which in a 2-pi domain, a 2-pi long domain, was steady state, well, we can see that we are no longer steady state. We get to a chaotic arrowhead regime. So we increase L, and what we got was intermittent arrowhead regime. So still not SAR. So we increased to 500. That's one of the beauty of our code. It's very robust and can really muster very large L and Weissenberg number. And we have a new code that can even do better on this. Here we got back to steady arrowhead basically. And I have run simulation on 4 times the size of the original domain. Okay, so this is 4 pi. I have simulation with 8 pi, and the same thing happened. Meaning, like, you can get into a system where even L equal 500 is not enough, but you can still increase L and get back to steady arrowhead regime. Okay, so effect of the Reynolds number. So those are 2 of the simulation that are presented in our upcoming paper. So we have Reynolds number of 100, Reynolds number of 3000, and we have arrowhead regime in both systems. But in fact, the Cambridge group with Miguel Benitez is actually showing that we have arrowhead at even lower Reynolds number than this. And then effect of beta. So remember, beta controls the shear thinning of the solution. And one thing that I found, I had never really played before that with beta. Typically use 0.9, 0.97. Those are the values that were used for polymer drag reduction. But I found that beta had a very much a stabilizing effect on the arrowhead. And destabilizing effect when beta is decreased, and destabilizing effect when beta is increased. Again, like it's presented in the paper as, well, this is what we observe. We haven't really had the time to investigate really why. The good news was we were able to get back the arrowhead, even for beta of 0.97, but it took a L of 500. So it basically essentially takes a large elasticity of the solution, when beta approaches 1 to get the arrowhead. So the last thing that I want to talk about is right now, you may feel that all the identification of the regimes have been really done by observation, and that's kind of true. So we worked out, more quantifiable ways to identify those regimes, and one of the way was to look at the symmetry of the flow. And so the symmetry of the flow is quantified by this correlation rho p that looks at the correlation of pressure between the lower half of the system and the upper, the channel and the upper half of the system. So if the flow is perfectly symmetrical for the steady arrowhead, we have a rho p equal to 1. And indeed, in our simulation, we achieve a correlation of 1. But we look also at the power spectral density of the signal of wall pressure and centerline velocity. So why did I choose wall pressure and centerline velocity? Well, that's trying to think about what an experimentalist has access to. And definitely an experimentalist has access to the wall pressure, and an experimentalist has access to centerline velocity with PIV or LDV. And I thought, well, if we can reproduce that experimentally, that could be of use. And obviously for the steady arrowhead regime and for the intermittent arrowhead regime, we see like a dominant frequency at 1, normalized by the centerline velocity, which is not surprising since it's the velocity, the convection velocity of the structure. So essentially, we can sort of figure out ways to discriminate between the regime based on the correlation and those spectra of the wall pressure and the centerline velocity, where definitely between the chaotic regime and the chaotic arrowhead regime, and it's more subtle for the intermittent arrowhead regime, where really the deciding factor is only the correlation. So if the correlation is not 1, then we are in the intermittent regime, which makes sense. So in terms of conclusion, what we've learned in all of this work, since we basically like since 2010, is that EIT is 2D, and it's really important because it simplifies our work. It is not surprising. There is actually really great work that was published around that time by Bofetta, Zaki, and Benti, I think. I really apologize, especially if you're on the call today. I really love their work, and we are about to reproduce it anyway in a Kolmogorov flow. And that work went a little bit unnoticed, unfortunately, but in fact, in their work, you can see an arrowhead. And so this is why we are in the process of reproducing this work. So we are confirming that there are exact coherent structure into the, and we in fact found one. We established that EIT is the result of energy transfer from small scales to large scale, which again makes the importance of the diffusion term and the Schmidt number that is used for the diffusion term absolutely critical to the study of this regime. And so far, we have found 4 distinct regimes, which include a steady one, to very much to our surprise. And ongoing future work, we are actively working on the identification of the source of chaos, or basically the mechanism by which chaos happens. We will move back to 3D very soon, and also investigating overflows. So, a conclusion that is not on the screen, but that is important, is that one thing that I'm learning every day when I try to investigate EIT and I try to derive theories and models for EIT is that many of the traditional turbulent theories do not apply to this flow because the physics is different. And so it is really important to keep a fresh eye on this and not try to fit turbulent theories, classical Newtonian turbulence theories, onto EIT. And in fact, if anything, our turbulence theories, let's not forget that they are mostly derived for high Reynolds number flow. And just as an anecdote, we have learned that the hard way with COVID, where this is a lot of my work right now, the transport of aerosol is in a regime where our models, our Reynolds models, and even our theories don't really apply, because it's a low Reynolds number, but yet still turbulent, and it's absolutely critical to predicting where dispersion occur. So going back to EIT, it is really important to not be biased and not hope that turbulence theories will totally apply. They may, right? But this is where one needs to keep an open mind. So I'm going to stop here and take questions.
So thank you very much, Yves, for the presentation. Yeah, as you said, let's just open the stage for questions. So whoever wants can open the mic and ask a question. Okay, maybe
I see that Martin has.
Go ahead.
Hi, Yves.
Hi, Martin.
I have a couple of questions, actually. The first one, I wasn't that 100% sure what is actually the regime of, so to say, inertia, elasticity, and viscosity. Because at the very beginning, you showed this arrow where, so to say, the lower Reynolds numbers were in the lower left. But I think on the slides you showed us, the Reynolds number was around 1,000. Mm-hmm. So maybe I missed something here. I mean, whether the results, essentially the simulation results, were they low or high Reynolds number?
No, that's a good point. Oh, what happened here? No, that's not at all what I want to see. Okay, I think I triggered something bad here. Okay, all right. Sorry, let me go back to that to this arrowhead, like to this arrow. So essentially,
yeah, exactly.
Yeah, essentially, I am in between Reynolds number 1 and Reynolds number 1,000. This is where I am. So the elastic turbulence is for, the original work of Victor was at Reynolds number 10 to the -3. Okay. Now, interestingly, Victor and we are working on that together. Has been able to show that it can carry that elastic turbulence to Reynolds number of order 1, if maybe even 10. In fact, even is starting to get higher. So that's another question that I didn't really get into, is whether elasto-inertial turbulence is elastic turbulence, and that's something we are actively working on. You have to remember that back in 2010 and 2013, when we published the PNAS, elastic turbulence was really confined at those very low Reynolds number. And so there was much discussion in the team of authors when we published the PNAS, how we were going to call this new regime. And we went with elasto-inertial turbulence because experimentally and numerically, it ended around Reynolds number of 100, 10, and so we felt, okay, so inertia should be important. If we had to rewrite this paper today, I don't know if we will say the same. Yes?
Well, so my basic question was more or less the, so to say, the physics saying, is it a balance? I mean, here in the lower left, where it says elastic turbulence, it seems it's, so to say, a balance between elastic and viscous forces, but as you go to higher Reynolds number, of course, inertia comes in. So how would you describe it? I mean, what is, so to say, the key balance in these terms?
So it's to me, I go back to one more. This is the last equation. That last equation, the pressure equation, applies whether you are at very low Reynolds number or intermediate Reynolds number. What it's going to change is the magnitude of Q. In fact, what we are seeing, even in our Reynolds number of 1,000, is that the Q term, the contribution of the Q term is not that large. So it's really about the polymer stress creating pressure perturbations that through incompressibility then create velocity perturbation, and those velocity perturbation through stretching by strain, the term in blue, sustain the stretch of the polymer, the stretching of the polymers. So that mechanism, to me, you know, that right now it's a conceptual mechanism, but that mechanism essentially should be the same in elastic turbulence and elasto inertial turbulence. I have started to venture into the world of elastic turbulence, and essentially the inertial turbulence, I think, has a strong effect on the elongation of those thin regions where polymers are stretched.
Yes, thanks a lot.
You know, but that, yeah. So it's going to take us a while to demonstrate that, though.
Okay. Any more questions?
Maybe I have 2 more comments, if you don't mind.
Yeah, go ahead.
The one thing is, I mean, you mentioned numerics, and actually we developed a discontinuous Galerkin solver for a high order scheme for viscoelastic flows. It was extremely difficult, I have to say, because we completely avoided diffusion terms in the transport equation for the for the constitutive equation. It was extremely difficult, and it still is difficult. So I'd be happy to share some thoughts on that at a later point. We also published recently a paper on singularities in viscoelastic flows that is part of a collection of papers on viscoelasticity that appears in Applied Sciences. There's a collection of papers on viscoelastic flows. If you're interested, I'd be happy to come back to you.
Please do, because
particularly this arrowhead kind of reminded me a little bit of these singularities that we find in the analysis. Just a curiosity.
Yeah, no, absolutely. We, I missed your paper, and I apologize for that.
No.
As far as the Galerkin solution, I understand your pain, but I am not surprised that you were successful, because we are, with different methods, we are seeing, like higher order methods, we are seeing success also. So yeah, there are new results that are coming soon, but I will definitely get back to, yeah, I would love to continue that conversation offline in the near future.
Sure.
Can I ask a question?
Yes.
So hi, first of all, thank you for a nice talk. So I'm curious to ask you, since you mentioned our paper and Stefano Musacchio, so I'm curious. Yeah, I'm curious to ask you which is the error that you found in our work.
Well, you have like the vorticity contours had really the shape of an arrowhead.
Yes, I agree. It has a shape which is very similar to what you mentioned, but we look just at the vorticity field, not at the field, the first normal stress difference.
This is why, like in a couple of weeks, I can get back to you.
Okay. So
with our new simulations.
I'm really curious.
Yeah.
Let us know. Thanks.
So any more questions? if you don't want to, or if you have any problem with Mike, you can write in the chat, and I can report the question from the chat just in case. In the meantime, I have a question myself. Oh, sorry. I have a question myself. So when you showed, let's say, a couple of results in which you were changing basically the regime by changing the L, so the extensibility parameter kind of thing. Would this be? How would you intend these results if you needed to interpret them as an experimentalist? I mean, the L is just a different polymer, or is a polymer which gets broken by a chaotic regime, or?
Yeah, so no, it's one of the complexity of the problem is the correspondence between the FENE-P model and an actual polydisperse solution is definitely not straightforward. And to me, I have yet to see really some like compelling relation or something that I would trust. Because at the end of the day, if you vary, say, like experimentally the concentration of your polymer, so you don't change your polymer concentration, effectively you change it L, Weissenberg, and beta all at the same time, like in different ways. So, you know, I must confess that right now I'm being very much of a numerical researcher. I have parameters and I play with them. I think it is important, and we have that in the back of our head, especially working with Victor, who is a pure experimentalist, that we need to come up with a better correspondence between experiments. So one of the challenge and the reason why I've gone back to the drawing board and looked back at different ways to simulate a FENE-P model is that Victor has Weissenberg number of 1,000, 10,000. And right now, my current method is probably the one that can go the highest in terms of L and Weissenberg number. But if I don't want to have simulation that will run for years because the time step is so small, I'm limited at Weissenberg number of about 500, right? So I don't have an answer for you, unfortunately, and that kind of pains me to say so. But yeah, this is something that we need to address.
And as we are on this slide, I actually have a second question based on the future works you mentioned. Because, I mean, you said that you want to get back to 3D flow. And I mean, if you consider the last regime, the steady arrowhead, basically you are 2D in a steady flow, you cannot admit any chaos in that kind of condition. But if you go to 3D, then you basically add the dimension which you need to kind of get some chaos. Do you expect that this regime would be stabilized somehow, or that you find something corresponding which is still steady in 3D, or I don't know, for some n number of reasons you think that this is just a 2D stuff?
So my one and only attempt at this showed that the 2D, I started with a 2D arrowhead, and it was quickly, the two-dimensional was quickly broken down by a spinalized streak instability. However, a structure that looked like the arrowhead was sustained for as long as I ran that simulation, and which was not as long as I wanted to, but was quite long. So, you know, I think what we're going to see is spatial intermittency. There may be a regime, but I don't see how. I don't see any mechanism in the polymers that will damp out the span-wise streak instability. So to me, it's going to be spatially intermittent. That's my guess.
Okay, okay. And if instead of somehow playing with a channel, you would generalize it to a pipe, I mean, do you think that's because you can get like the other curvature which can play for the hop stress kind of thing? So
yeah. Yeah, we have those are also plans in the work to look at the pipe, definitely. And there we might if we have an arrowhead that really fills the pipe, we might get something steady.
Okay, okay. So that's yeah. Thanks. Any more questions? Just once again, feel free to unmute your mic and ask a question, or you can write it in the chat and I will report it. Okay. Okay, so this doesn't seem to be the case. So thank you once again for the presentation of today. Let's thank our speaker again, and I hope to see you soon. To see you all next week. As I said, I will soon upload probably by this evening the seminar last week, and the seminar of Yves will be uploaded within a week. So thank you all, and hope to see you next week. Thank you once again.
Thank you so much for the opportunity. You have a few minutes to...
Thank you. Bye-bye.
Thank you, Martin. I will contact you back.